Before we begin, do you have any questions?
Yeah, I have a question on the chapter 1 worksheet. Number 34, it says like, what is a time series? Sketch an example of a time series. I was looking in the textbook and I was having trouble finding this. So what is that, or where can I find that?
So this is kind of near the end, huh?
Mm-hmm.
So for instance, if you take a look at page 13, that's a little bit of a time series.
Okay.
So anything that you're dealing with reference to time as the independent variable on the horizontal or the abscissa, that is when we're talking about a time series. So you're basically plotting out how does weather change over time. So let me show you something here. Long as this is a weather class, right? I mean, we do weather in this class, supposedly. Let me throw you guys over here. And you see my screen? So here's an example of a time series. This is called a meteogram. And what it does is it shows you what's going to be going on over the course of the next several days. And each one of these things is a model solution. So the models from before showed a very cold morning. I think we got down to like 2 degrees at DuPage County Airport. And then we're coming up. So here's your plot of temperature versus time. And then we get warmer on Saturday, and then we get around 30, and it comes back down. So this is a time series. In this case, it's called a meteogram because you can look at apparent temperature, which is like wind chill. Look at dew point forecast, winds, speed, wind direction. And then this one, which is a snowfall total. In case you haven't noticed, the latest models are bringing in 8, 10, maybe 12 inches of snow coming in this weekend. This weekend. So we're going to have to see how that turns out. So this is a time series that some of you may like. How many of you like snow? How many of you do not like snow? Yeah, so that's probably not what we all want to see if you don't like snow, but that's what it is. Okay, Ian, you're here. Hold on.
Yeah, sorry about that.
No, that's okay. When I take attendance, sometimes I take it right off the bat, and I just want to make sure you're counted in here. So anybody else? Tucker, you here yet? Tucker, Shannon, or Nathan? Nope. Okay, so that's the answer to that question, Lena. So if you wanted to, you could even just kind of Google something like that, or a meteogram. That would be fine. You could look at that. That's a time series.
Perfect. Thank you.
Okay. Because, it's kind of that you bring that up. I think that's important that we kind of look at this a little bit. And we say, well, when we talk about most graphs are going to be, like this. And typically speaking, the independent variable, the one that you control, and that's important that you know that, right? It's you control. The independent variable goes on that axis and the dependent variable on this axis. And then a point says, if, the way that you read a coordinate or an ordered pair is given this value on the independent variable, it corresponds to that variable on the dependent, or that value on the dependent. So it's a correspondence, and that's really the word you should use. The independent variable, given that, you control it, you tell me what you want it to be, I'll tell you what the dependent variable is. Now, one of the ones that we do in class is we'll often go the height and the pressure. Now the difference is the pressure depends on how high up you are. The height doesn't depend on the pressure. We do this, we switch these independent and dependent only when we're dealing with height, because it makes sense that height is up and down. So that's the only time that we're going to probably see that change. But this is kind of important that you do this stuff. So independent variables are usually location, which would be variables like X, Y, Z, and time. It's not always. I mean, there's other ones too, but those are the standard ones that we're going to be dealing with. So the location is, we're going to mark location X, meaning because X marks the spot. Z is a vertical location up on the vertical axis. That's it. I am not going to differentiate X and Y, although I would do that in a mathematical class, and certainly higher level classes, we're going to separate X and Y. When I talk about delta X, which is a change in the X value, this is a change in what?
Location.
It's a change in the location, which makes that's equivalent to a distance. Here's something important. Listen to me close, ready? Delta X is not a change in distance. It's a change in location, so delta X is a distance. What would a change in distance look like? Isn't that a change in the distance? So how far do you live? I live 5 miles away. No, I live 7 miles away. That's a change in the distance. Now, for those of you with calc, that's a second derivative. But that's the way you would do it algebraically. So what we're saying is that delta is an algebraic, oops, that's horrible. Algebraic, and D is calculus. It both means a difference. So when you see D or delta, so in other words, if I were giving you a test and I said, let me do it this way. What is this? What's the numerator? Say it out loud.
Distance.
Over.
Change in location over change in time.
Okay, you could say change in location over change in time. You could say distance over a change in time. That would be fine. But that's the same thing as dx dt. And we go. Come on, everybody.
Oh, that's a question.
That's a question.
That's a question. Dx dt. So these two things are as far as you are concerned. Now, one day we're going to talk about the difference. There's a difference between this, and there's a reason for it. We're not going to do that for like 12 weeks. Okay? So as far as you are concerned, this and this are the same thing. If I'm asking for this and you give me this or vice versa, I'm okay with it. Okay? This one, however, when I do this that's a question. How does the location change over time? Now, the thing that I want to talk about really quickly is this. What did you call this? What did you say this was in the pink?
A change in time.
What does that mean to be a change in time? What's another word, a better word for a change in time? And so what does that mean?
Lapsed time.
As time goes forward.
So what do you call that though? And somebody else said something I didn't hear.
Elapsed time.
Elapsed time. There's maybe a better word. Aaron, you got one?
He says lapse.
It is an elapsed time, but there's a shorter word. One of two things that you could probably say that would make more sense. Like right now, what time is it? It's 1:16. 30 seconds now, 30 seconds from now, it'll be 1:16 and 30 seconds. That delta T is 30 seconds. That's a what? What's the word I would say? It's either starts with a D or a P. An elapsed time is a what? What's the word?
You know?
Say it.
Duration.
Right?
And
Is
period.
that a duration? What's P? What could you have said?
A period of time.
It's a period of time. So how does your location change over a duration? Over how much time has elapsed? Over what period are we talking about? So for instance, if I said I go 60 miles, that's how far I've traveled in 60 minutes. That's saying I'm going 60 miles per hour or 1 mile per minute, that kind of thing. So just remember that delta T is actually a duration. It is not the time. Like if I said what time it is, you don't go 30 seconds have elapsed. You go, it's 12, 17, and 22 seconds exactly. Then now it's passed. Does that make sense to you?
Yes.
Okay. Any questions on this? Okay. Anything else? Did you look? Okay, so take out your lab like you were supposed to do. So in the, what is this? By the way, did you guys get my email?
Yep.
Did I fix this? Did you print out the fixed one?
Aaron had already done the other one.
And it's fine. There's really very little that's changed. It's nothing big and important. If you did it on the PDF, that's fine too. Now, did you read through this? How many of you did not do what I asked you to do? You'll have to be honest with me. Any reason? Ian, Zach, what's your reason?
I saw the due date was like the 31st, so I was gonna do it over the weekend.
Well, and that's fine. Ian, what about you, bud?
I also thought I had a lower due date. I didn't know it was due for Thursday.
Well, I did say, so I just, these are the kind of things I really want to make sure. So a lot of times I'm going to tell you, I want you to do this for the next class. You're not turning it in because we can go through it and you can fix it. But there's sometimes I want you to do the work on it. So Avi, what did you end up doing for this?
I didn't do it.
You didn't do it either?
No.
Why? Why not?
I thought that was the due date was longer.
Tom, did you do it?
I did not because I haven't gotten my textbook and I didn't know if it would be covered.
Okay. Lena, I know you did it, right?
I started it. I'm having trouble on it. I know last semester when we did stuff like this, this specific topic, I struggled. So.
Okay.
That's why I wait
Sam,
more.
how about you, bud?
I thought the due date was a little bit further out.
Okay, Nick, how about you? Nick Zucchero.
Yeah, I didn't do it either.
Okay, Zach Medlin.
No, I didn't do it.
Tim.
I went through the first few parts of it and then kind of got stuck.
Julia.
Yeah, I did like half of it and then I was having trouble, so I didn't finish it.
Okay, Ryan.
Also started it, but I didn't get through all of it. I was having some trouble too.
Isaac.
I ordered my textbook about a week and a half ago. I still haven't gotten it yet.
Okay. Aaron?
Yeah, Aaron finished it.
Aaron finished it. Why did Aaron finish it and the rest of you didn't do anything on it? See, this is, any of you guys psych majors? See, this is what's kind of interesting to me. It's like, I don't know, I'm not going to yell at you today. Sometimes I yell, I get angry because I want you to do well. I want the world to be a better place, and I think the world is getting stupider by the minute. Okay, and I don't want that to happen. So I could give you negative, like by punishing you. I like to give positive reinforcement. I can't give positive because you didn't do anything. Was I clear the other day that I said I wanted you to go through this as much as you could to be prepared for it in class? I think I was clear. So why you didn't do it is just beyond me. I don't understand this. You're in college. The great thing about college is that you're supposed to do stuff because it's the right thing to do. You're not in high school. If you're in high school, you're forced to go to high school. You got to go to high school. Mom and dad say, you got to go to high school. Now you're in college. There is no mom and dad to worry about. It's up to you. You make the choice. And when I give an assignment, I'm not doing this to punish you. I'm giving you because this is how you learn, and I want you to learn. So it's just really hard on me, guys, right? I mean, look at what I'd rather have done is take about 10 minutes, go through where your problems are, go, oh, this is fine. Now, how do I do that? You haven't even found the problems. Some of you, maybe a couple of you. Julia, what problem did you have?
I was struggling when I got to the part about lapse rates. That was confusing me.
Okay, so up to that point?
Yeah.
You were okay.
Mm-hmm.
Where were you at, Lena?
I with the part, hold on, let me pull it up. I got confused on where it says write the relationships for each pair of variables, substituting A, B, and C. That's where I got stuck.
Okay. I'm doing this. I'm going to manually assign you to rooms. How do I do this? Assign. Abby, Aaron, Isaac, and Zach. Okay. Add a room. Sam, Tom, Julia, and Ian. And what am I going to do? Assign the other 5 of you. I want this lab done in 45 minutes. When I come into your room, you better be working on it, or I'm going to erase you from class. Am I clear?
Right now.
Yeah.
So how are you guys going to start this now as a group?
I don't have my book yet, so
Isaac, it doesn't matter because this has nothing to do with the book.
You don't need
This
the
is
book.
this is an assignment that we went through the other day, so you don't even need your book. It's not in the book even.
okay, thank you.
So how are you guys gonna work on a Zoom collaboration like this to do this lab?
Do it like one problem at a time. Read it through and then like discuss it.
Okay, how do you want to read it through? Do you want to read it out loud, one of you?
I mean,
Or do you want to just take a few seconds and read it and then come back and start the thing? I'm not, this is not a test question. I'm just wondering how you're going to do it. So you guys make that decision. Now, Aaron, you've already got that. Did you have any problems, Aaron? Did you get most of the answers?
I think most of them, yeah.
Okay. Well, then, Aaron, you kind of oversee what these guys are doing. And Aaron's already got this done. So if you guys run into problems, ask her, okay?
okay, thanks.
Thank you.
Wait, where am I? I got to figure out how to get to my other rooms real quick. There we go. Okay.
I mean, you got through most of it pretty well. And do we just read it out loud, or do we want to all read it together by ourselves?
This was the reading assignment, right? Not. I thought it was a lab.
No. This is the lab, right? This is the mathematical lab, the one that I sent an email about and said this is due. But I like what Ian said. Are you going to read it out loud together? I think that would be okay if you do that. And then answer question by question and talk about it, because we got to see whether you understand this. Now, in every group, I put people I think that should be able to get this stuff. You know, so different skill set as far as I know from you guys. So Ian, you made a good leadership decision. Should we do it this way? You guys decide. Okay, see you soon.
Yeah, I guess we could.
Yeah, because in the background, it has that as like an example. So I don't see really why not.
I mean, I guess, like, why not? It is something.
It's an equation.
I can't come up with anything better, so.
Yeah, honestly, I don't know what else to put there. So I don't know. That's what I put.
I'm putting it.
What's the question?
Wait, hold on. For the write down an example equation, because in the background it says like A equals B divided by C. So like, could we do that as an example, or do you want something different?
Well, no. Look what it says. What's the sentence before that?
Oh, put in actual numbers. Oh, okay.
Okay.
Oh, okay. So,
are you guys able to type on it though?
I am.
Yeah, I can.
All right. So it's me.
Okay, so Nick.
Yeah.
You open up the document just now?
Yeah. Well, I opened it in the last class too, but yeah.
Okay, but this document, it should be something on your Microsoft. If you're using Word that says enable editing.
Yeah. I pressed enable editing. I'll close out and try to open a new one.
Yeah, open the new one because it's a doc file. I put a doc in PDF. You can't do the PDF, but this one you can.
Okay.
So what are you going to write down?
Well, we could just write down numbers, right?
Yeah. So wait a minute. What equation?
So like 2 equals like 2 over 1.
Make them bigger and make them all different. Doesn't have to be, but do it.
8 equals 16 over 2.
Okay.
Yeah, the one I used was I did A equals B over C, and then I did B equals 20, C equals 5, A equals 4.
Yeah, right.
I don't know if that's how simple he wants it.
Well, here, let's take a look at what you guys are doing here. I can't share my screen, can I? No. You don't see my screen, do you?
No.
Well, what you do, like, what does it say that you're supposed to do?
Write down an example equation.
Yeah, but no, look back in the paragraph says first A, B, and C. And then read that paragraph slowly. So Zach, read it out loud, would you?
Yeah. First, A, B, and C do not mean anything. Secondly, they can either be constant or variable. In any equation, it is important to realize that we can only deal with 2 variables at one time.
Okay, stop. So how many variables are in that equation?
2. Right?
A equals B over C.
There's 3.
So there's 3.
Can you deal with an equation with 3 variables?
No.
So what do you have to do to one of those variables?
Define it. Like give it
No.
a value?
Look at what it says.
To make it constant.
Yeah.
You make it, right? It's either a variable, which means it can change, or it's constant, which means it doesn't. So the first thing you have to do is you take that equation and you make one of them constant. So you wrote numbers. One of those three numbers, keep it the same. Then what do?
Put in the other variables.
Well, what do you have the other variables. You've already got an example. You do what to one of the other numbers?
Solve for it.
Yeah, change it, right? It says the point is to see what happens to the other variable when the first one is changed. Decide which one of the variables, either making it greater or smaller. So I'm going to leave you with that, okay? You should be able to figure this out now.
That's 3.
Yes.
Right?
3.
Yeah, so is that directly proportional
Uh,
or inversely?
I think it's inversely.
Wouldn't it be?
What did you guys write down?
Wouldn't it be direct?
We're working on page 2.
Right. What did you? There. Can you see my screen?
Yes.
Right, okay. So did you do this?
Yeah. Would that be A equals B over C?
Well, that's not an example. Look what it says here, right? That's what it's saying for you to do.
If you're still having problems, yeah.
So write down an example with actual numbers.
Yeah. Okay.
So what do you got? Give me one.
Like 10 equals 20 over 2.
Then what? When I have this equation, how many variables do I have?
3.
3.
Okay, now, what does it say up before, in the page before? What does it say in this paragraph?
Point is to see what happens to the other variable when the first one is changed.
Okay, before that even, look at the stuff I highlighted in gray.
If any equation, it's more important to realize that we can only deal with 2 variables at one time.
And you said that there's 3 variables, A equals B over C, 1, 2, 3, right? So I can only deal with 2 of them, so what do I have to do to one of those variables?
Take one out.
How do I take it out?
Division.
I can't just take it out, right? That doesn't make sense. 10 equals 20 over 2. I can't just go 10 equals nothing over 2, right? It doesn't work that way. What you have to do, it says in the next line,
It says you have to hold a value of a constant. You change the value of one of the variables.
okay, so which one of these 3 numbers am I going to keep the same?
2.
Okay, so
2.
I've made C constant.
Right.
Now you change one of the other ones. So which one do you want to change?
10.
Well, let's make this one just for the hell of it, because it might be easier.
20.
Let's make that 30.
Oh, okay.
So what's 30 divided by 2?
15.
So 20 got larger.
Right.
10 got larger.
Right.
So that means as this variable, B, gets larger, A gets larger also.
Right.
That's what?
Okay. That's directly proportional.
if
it's
C,
If C is constant.
that's what you have to say.
It's directly proportional if C is constant.
That's how you do that. Now you change the other variables to figure out all the relationships. Because look, how many sets of relationships are there? Well, there's going to be A and B. There's going to be A and C and B and C. So what are those relationships? They're either directly or inversely proportional.
Okay, yeah.
Okay.
Yeah. All right. Yeah.
So you guys keep doing that.
Right.
Same. You just like swap out the letters.
Oh wait, really?
Yeah. Like the first three I did for the equation that's pressure equals force over area, and you just like change the
A and B and C values of whatever those
so
are.
that like I don't know how to explain it, but
well, okay, Julia, try it again.
So basically like the first one I have like P equals F over A, because that's like the normal pressure equals force over area. And so then I changed them around so that you would get force equals pressure times area. So you have like the different equation to get force.
Oh,
And then
okay.
for area, you would have pressure over force.
Okay.
That makes sense.
Why are you doing that?
So that like it changes it so that you get the I don't know what I'm trying to say. Okay. Like, because when you're doing the equations, like, I guess I'm thinking like ahead, like you have two numbers and you have to solve them.
But
so I flipped the equations so you could solve it.
What you want to do is you want to do this kind of thing. You're looking for A equals B over C, right? Now, I know that B is equal to C times A, right? That's simple algebra, but that's not what I want. That's not what I'm needing to do. I'm needing to say there are three sets of relationships. Those two, A and B, those two, A and C, and those two, B and C. I don't need to change them to know what the relationship between two variables is. Now, the question is, if I said, what's the relationship between A and B? What are the possible answers you can give me? What are the possible answers you can give me?
Directly proportional or inversely proportional?
Those are the two answers. So you have to first say, well, what is the relationship between A and B, A and C, and B and C? Once you know those relationships, when I say something like this, don't I have, isn't this A, B, C? Isn't pressure A, and isn't force B, and isn't area C? I should be able to know the relationship between pressure and area, and pressure and force and area. But what do I have to, when I deal with the relationship between these two, what happens to this guy? What do I have to do to this guy?
It's to remain constant.
So you have to say, if the area is constant, then what's the relationship between pressure and force?
All right.
So you have to, now, so once you do that, and so did you get the number thing? Did you try the numbers for this one? Did you substitute the numbers in as an example?
Oh yeah, Julia did. Julia did.
What did you write down? What was
So
your-
I did like, I don't know if this is right, but I did 0.5 for A, and then that's equal to 1 for B and 2 for C. So like 0.5 is 1/2.
Okay, that's fine. A little bit more complicated, but that's fine. Then what did you have to do first?
Well, basically what I did was just like up them. So then A is 1 and B is 2. And then C stays the same as 2.
Okay, so what you do first then, right, is you say, all right, I'll keep C constant. So that's what you're saying, is that stays the same.
Yeah.
And then you control whatever you do next, right? You control this. So you say, well, if 1 goes larger to 2,
yeah,
then what does 0.5 become?
1.
So B got larger. That means A has to get larger.
Mm-hmm.
If their change is in the same direction, we say that's directly proportional. So you would say A is directly proportional to B if
C is constant.
So you have to say that. If you only say A is directly proportional to B, that's half a point. You have to say if C is constant. So once you do that, then you go here and you're like, well, okay, now I'm going to use the same thing. So what's the relationship between pressure and force?
Directly proportional.
If
the area is constant.
Okay. And that's how you do this.
Okay.
Okay, keep going.
Thank you. All right.
How's it going, guys?
We're working on the second question, writing down the relationships for each pair of variables.
Okay. So I'm gonna let you do a little bit of this stuff, okay? You guys working well together?
Yeah.
Yeah.
Good deal. How's it going?
Pretty good. You were just in here.
Okay.
Right.
Working well together?
Oh yeah.
So Paul, I found out why I can't edit the Word documents. I'm not signed in to my DuPage account.
Oh.
There it is.
Okay, can you fix that then?
I can, but I forgot my password.
Oh, well, they have a help desk, so you can do that. So right now you just have to write it out on paper.
All right. I mean,
Is everyone pretty much done with that one?
What did you? Which one are you done with?
Now I'm like totally lost my spot. Just the one where it was kind of the explanation on pressure and density.
Okay. So I'll let you guys go a little bit longer, okay?
Okay.
I don't know what's being recorded. Make sure you got your names of everybody because you're going to have to finish this up. Now, this is the kind of stuff and the time that you should have spent individually reading. My guess is that you don't really read stuff. You go to answers, right? I mean, I've dealt with students for 30 years. I kind of know what to expect. See, this is why I'm not really mad, because I don't ever expect, I mean, here's what I go crazy at. I want my classes to do what I say, but I never expect them to. It's kind of a sad statement on our society, isn't it? I was thinking, you guys were in your group, I was thinking about Alexander Hamilton. Do you know he was inventing financial systems and working for banks and stuff when he was 17? And it's not that he was that great of a genius. I mean, he was smart, obviously, but that's what that society was like. People used to do stuff and their brains were actually really good. Am I right in thinking that you probably go right to the trying to answer the questions without really reading and understanding? I think that's probably the case. Try not to do that. Try to read and understand. Do you have any questions about A equals B over C? What is the relationship between A and B? Tim, we'll start with you.
I said it's directly proportional.
What's wrong with his answer?
B needs to be constant.
A is directly proportional to B if C is constant. You've got to put that in there. Okay, what's the relationship between A and C? Isaac.
A is inversely proportional to C if B is constant.
And that's very good. And what's the relationship between B and C? Brian?
B is directly proportional to C if A is constant.
Okay, that one's a little bit different, right? That's kind of a weird thing. So, but those are the correct answers. Now, once you get that, I'm telling you, we will see that equation at least a dozen times in class. Everything can be set up into that thing so that you know the relationship to the variables. But the difference now between knowing the answer and, well, here, let me do it this way. So let me share the screen. I'm gonna put you guys. I hate this. This is the one thing about Zoom I don't like. I don't like that I always have to resize you guys every time I do this. I want you to go to what I want you to go, like this. Okay, so watch this. Here's a box of air. Box, box, and I'm going to draw some straight lines because I can make a nice simple box. And I'm going to use, the first one I'm going to deal with is density. What, did we do this? We did this, right? What's this Greek letter? Did I do this with you yet?
Oh.
This is what Greek letter is this? This is Greek letter rho.
Rho.
Okay. Now everybody, look at my screen. Look at the screen I'm sharing. Watch the way I draw the letter rho. Up and around. This is how you draw the letter rho. This is not how you draw the letter rho. Do not go down and around. That's probably how you draw the letter P. Don't do that. Go up and around. Smooth letter rho. When you draw the letter P, it needs to look like this. There needs to be a stem on it. So when I see this letter and this letter, there is no question. Rho, P. What do you think P stands for?
P.
Pressure.
Pressure.
Pressure. What's rho? Density, right? Rho stands for density. If I said, hey, this box is a density, what is the density? Rho. What is the definition of density? If that's in your lab, right? Somebody read it to me.
Mass divided by volume.
Okay, right? This is what we're talking about. And what does this box contain?
Particles.
And what are those called? Those are molecules, right? Do you agree that molecules have mass? The mass of this box is because of what is inside of it. So we could have said the number of molecules instead of mass. Do you agree that the box has a volume? Tom, what's this side? How long is this?
Delta X.
And what's this? What do you think it would be?
Delta Y,
And then this.
delta Z.
Okay. So really, the volume is delta X, delta Y, delta Z. Now, it's kind of interesting because we could say that sort of, you could use this as a differential, being it's a change in volume, whatever. But if I make this side longer, I'm really saying I'm going to, don't draw this. Delta X has been changed. And now the volume gets changed. So the volume changes when I change the length of any of these sides. So Tom, because you're a math major, I expect that when you draw stuff in a math class, you do not do the X, Y, Z stuff. You will be a better person if you do a deltas. Because I know sometimes they go X, Y, Z. And I don't, that's not good. That's my opinion, but I'm pretty sure I'm right. Okay, so anyway, there's a volume here. Do you agree with this? So given this, do you agree this, what's A? Everybody on the count of one, on the count of three, tell me what A is. 1, 2, 3.
Rho.
Everybody, 1, 2, 3.
Density.
You could say rho, you could say density, right? What's B? 1, 2, 3.
Mass.
What's volume? That's C. So what is the relationship between density and mass?
Directly proportional.
If
volume is constant.
So that's important that you get that. That is correct. That is what we said with A equals B over C. Does everybody understand that? Okay, so now here's the thing, because we're going from math to science. Do you see that in the box? Tell me how this changes in the box, in this picture. Describe what you see to know that relationship is true. So, Julia, how about you?
Like how it's related?
Well, do you agree that density is directly proportional to mass if the volume is constant? But now I want you to show me what you see with this picture.
Okay, well, if the volume is constant, then like the box would be the same size. So then if the density goes up, then the mass of the particles also goes up.
Do you think that's the best way to say it? If the density goes up, then the mass of the particles goes up? Or would you rather say if the mass goes up, then the density goes up?
Yeah, that would make sense.
Okay, because I mean, it's not that you're wrong. I just think that makes more sense. Now, how would the mass of those particles go up?
If there was more of them.
Okay, so imagine that I put more particles in here, more molecules. Would you agree that this box is now more dense?
Yeah.
Same volume, because I like the way she said that, right? Okay, so we imagine that the size doesn't change. Correct. We put more mass in there, and we have a greater density. Okay, let's do this. What's the relationship between mass and volume?
Directly proportional.
Describe it. If
Density is constant.
okay, so describe that, Tom.
Directly proportional to volume if rho is constant.
But describe that in the picture, Sam. Go ahead. Like, what? How would you see that? What would you do first?
I mean, that's all I have written down.
No. I'm not talking about writing it down. I'm saying looking at that box, describe what you just said. What do you think, Nick? You want to try it?
Oh, me? Am I the only negative here?
I think you're the only. We have
Yeah, no, I'm not really sure. I don't know, like, I don't know how to like say it in terms of what I would do, like with the box. I would have just said like, masses directly, or yeah, what he said.
But I want to show me what's going on in that picture when those things change. So you're right. And see, here's the thing, folks. You guys are thinking you're writing down the correct answer, and you could memorize that, but that's a bunch of garbage. Learning is not memorization. I want to know, how does that picture change to keep the density the same? And what do I have to do?
The mass and the volume would be changing proportionate to each other.
So show me one. Give me an example.
So let's say if the density is the same, let's say the volume gets larger.
Okay, so watch this. The volume gets larger. Now, if the volume got larger and that's all that happened, what is staying the same?
So what did you say? Sorry.
If I made the box bigger, what's staying the same in my picture, in my head? Isn't the number of molecules staying the same? But if I made the box bigger and thus stayed the same, what would the density do?
Well, it would go down.
It would go down. So instead of having the density go down, I want to keep it the same. So what do I have to put in the box?
More molecules.
Exactly. That's how that works. What's the relationship between, well, I guess we already said density and volume is they're inversely proportional if the mass is the same. So I take this box, I make it larger, and the density is going down because the same number of molecules are occupying a larger space. Okay, do me a favor, guys. I'm going to do this for a sec. I want you to get close to the screen. I want to see, put your hands like this, put your head on your hands, because we're going to have a little conversation here. I'm going to tell you something important, and I want you totally focused on what we're doing. There's 3 levels at which you learn. The first level is I say something, and then I ask you, do you understand that? And you go, mm-hmm. You know, because most of the time that's what happens. Do you understand something? And you know what the most common response from people is? You don't even nod. Most people go, nothing. They do nothing. The good students like you, Ian, are like, mm-hmm, I understand, right? Then you go home and you look at your notes and you're like, I don't know what the hell's going on. And then you come to me and you say, hey, Paul, when you said it, I understood it, but I don't understand it on my own, right? That's a bad level of learning. You're never going to get a good grade on a test if you're at level 1. Level 2 is what I call the light bulb moment. When you're like, oh, I get it. And you, when I watch people learning and they get something difficult, they actually smile. They're like, oh, I think I get it. So your friend comes to you and goes, oh, that's great. Hey, Julia, explain that to me. And you're like, I can't. You're at level 2. You're like, I think I get it in here, but I can't express it to somebody else. So what do you think level 3 learning is all about? Getting to that point where you can explain it. Now, here's the thing about explaining stuff to other people. Nobody does it right the first time they try. Never. It's an amazing process what's going on in your brain, because this is how people are when they try to explain something they've never explained for the first time. They stutter, and their eyes are going up because your brain has to process. So your eyes go in different locations. You're like, oh, and then you'll say like, oh, that's not right. It's amazing when I have people explain stuff, they'll go, that wasn't very good. They'll say that to themselves, and then they'll do it again. It's like riding a bicycle. Do you remember learning to ride a bicycle? Doing something for the first time? Everybody does it the same way. What's the first thing? Who taught you to ride a bike?
My grandmother.
Your grandmother. Oh, that's interesting. Most people have their mom, dad, right? And so they're sitting there with holding the back of your bicycle and you're riding. And at least for me, and I'm pretty sure this is true for most people, the first thing that happens is they let go and the kid doesn't know that they're not being held onto. But all of a sudden they become aware, mom, dad, grandma, they're not behind me anymore. And then what do most kids, almost all kids do at that moment?
They freak out.
And they do,
Panic.
and they fall. Do you know why most kids fall when they do that and freak out? What do they stop to doing?
You stop focusing.
Well, no, when you're riding a bike, what makes a person fall on their bike? Stop pedaling. Most of them stop because they just don't pedal. They freak out. They stop doing their stuff. They get slower and slower and slower, and you can't balance unless you're moving, and you fall over. Right? Kids do that. Now, kids are little, and the bikes are small, so they don't really get hurt. Most kids don't cry. Then they do it again, and then all of a sudden, something in their brain goes, wait, if I pedal, I stay balanced. And all of a sudden, the kid goes, I know what this feels like. And as soon as they get there, I don't need mom or dad or grandma. I'm riding a bike, and they get it. And then do they ever forget the bike riding in their life? No, they're like, I know, because your brain says, I know what I'm doing. I figured it out. That's what you need to get to in any class. This class especially. You need to get to your place where you're like, your brain goes, okay, I understand this. And I'm going to ask you to explain things, and you're not going to do a good job. But you will. The more that you do it, the better you will get. No kid learns to ride a bike without falling. Eventually, they stop falling. That's called learning. If you're not getting to level 3 learning, you're missing out on fun. Because that's where the learning is it's amazing to me, all my students. This class is really hard. And they all go, your class is the hardest class I've ever taken, blah, blah. But they like it because the reality is your brain wants to learn badly. It wants to be smart. Most people don't have a good brain and they're pretty dumb up there. But in here, I want you to be smart. Okay, now I'm going to go back to breakout rooms and I want you to discuss pressure equals force over area. And I want you not just to give me, because you probably said pressure is directly proportional to force if the area is the same, but I want you to draw a picture or I want you to look at it and say, well, what's going on? I want you to describe it. So I want you to think about this in terms of this picture. So pressure, no, you're not watching, you're not saying anything, are you? Hold on. Share. Pressure equals force over area, right? That's what this says. A equals B over C. So I want you to describe in the breakout group to other people what you see is happening. And I want to see how well you can figure this out on your own. Does that make sense to you? Do you understand what I'm going to ask you to do? All right. I'm going to, this time, I can go. You want to go back to the room you were with? You like those people?
Yeah, that's fun.
All right, let's do that for today. Next time we'll do different stuff. But I'll open the rooms. I'll see you soon. We'll all come back together in about 5 minutes, less than. Hi, Aaron.
Hi.
I guess I've been recording this. Oh well. I've been recording a lot of empty space. I don't know how somebody has to tell me how the recordings go when we're looking at breakout rooms. I don't know where it records. Last time I paused it, this time I didn't. So what do you think? Did you get this? Let's get everybody back in here first. When I share my screen what do you see right now on your screen?
We see the grid right now.
You do see the grid of people?
Yeah.
And you see the box on the grid, right?
The box on the grid, yeah.
Okay. So when I go to this epic pen, I lose you guys. So let me do this. Okay, so Ian, you seem to be doing well today. So go ahead, describe for this pressure equals force over area. Describe those relationships.
So we decided to relate it to like a plane. So like if area of a plane is constant, then pressure and force are directly proportional.
Okay, so let's do this. Let's look down here at a plane. Because the box is actually just how many planes?
Are you drawing right now?
Yeah. Oh, are you seeing that?
No.
Oh,
I can't see it.
What do you see on your screen?
we still just see the grid.
Yeah.
You don't see the box here?
No, I said yeah, but I thought you were just talking about the boxes of our pictures. I'm sorry.
Oh.
I don't see your drawing.
Hold on a second. Well, I'm gonna have to move you guys over here then. Sorry. Now what do you see?
We're still on grid right now.
Oh, maybe. Okay, now you see.
Yeah, and now we
What
see
do you
a
see
box.
now?
Now we see.
A box on blackboard.
Do you see the grid of people?
No. Now you're screen sharing.
Oh, okay. So, because right now my grid of you guys is right here. Here, that's why I put you on a different screen. So you see the box now?
Yeah.
Yeah.
Okay, so here's the box. Let's go to the announcements. Easier, whatever. And here's the little plane. So this is the plane. So you guys were saying you see a plane. So what are you seeing?
Oh, like what would we see as we're?
Don't you see molecules hitting the plane?
Yeah.
That's what the force is.
The force.
Okay. All right. So go ahead.
And then yeah, as force increases, so would pressure, while the area is constant.
So in this area, you keep that constant. So the molecules hit harder. That's a bigger force. The area stays the same. So that means the pressure goes up. So the pressure is going up, the force is going up. Okay. And then what else can you say?
And then also, if pressure is constant, then force and area are proportional or direct proportional, which basically means that the area and force is whenever more molecules are hitting, or the same amount of molecules and same amount of area is getting hit, and then as it increases, yeah.
That one is all like impossible because I don't know if you can visualize. If they hit harder, this area gets bigger. I don't think that doesn't make sense to me.
I guess as the plane would fly faster, the molecules would hit it harder.
Why don't you look at this box? You agree that these molecules, if they hit harder, what would they do to this box? Zach?
Would they make it expand?
Wouldn't it make this box expand if these molecules, So I want you to take a look at just this wall over here. There's molecules hitting the wall of the box, trying to move the wall which way? To the right. So there must be something out here. There must be molecules out here that's pushing and trying to push the wall inward. Don't you see that there's molecules trying to get out and there's outside molecules trying to get in? So if this molecules hit harder or force, then which way would this wall go?
Outward, like
Right.
expand out.
Wouldn't it go to the right? It would go from left to right. Well, what would this wall over here do? Which way would it move?
To the right.
Also.
Well, don't forget, these molecules in here are moving faster, so they're hitting the wall harder. The outside molecules are hitting the wall here. So which molecules are hitting the wall harder? Inside walls or the outside wall?
Inside.
So which way would this wall on the left move?
It would move to
To the left, right? So look, you see me? It would, the walls would move like this. What would these walls do?
They would
Move outwards.
And then these walls would.
Move upwards.
So wouldn't this box get bigger?
Mm-hmm.
Expand. But so when we talk about area of the box, what area are we really referencing?
The area inside the box.
What do you call that? There's a name for that
Volume.
area.
Is that the volume or?
It's not volume. It's the surface area. It's the surface, it's the area of all 6 of those walls added up. Now it's related to volume. Do you agree that if the volume gets bigger, the surface area gets bigger?
Yeah.
So what you're saying is if I hit the molecules hard, if the molecules hit harder, and I want to keep the pressure the same, then the box is going to get larger. But if the box gets larger, just because the molecules are hitting, what does the density do?
It becomes less dense.
So isn't there a relationship between pressure and density? If the pressure goes up, what does the density become?
Lower.
It goes down. But the question is, there's no equation for those two, not yet. Besides, I don't know what the other equation is. I'm not sure exactly what the other variable to stay constant is, but I know that pressure and density are inversely proportional. If the pressure inside that box goes up, the density, and it pushes out, the density gets less, assuming the box does what? What does the box have to do for that to be true? Doesn't it have to expand?
Yeah.
Now, what if this box were solid? A solid box. In other words, it's made out of, let's say, metal or wood or something, and it doesn't expand. Do you see that the molecules, if they move faster, would not change the volume? Wouldn't change the density. It would just hit harder. So if the molecules hit harder, what's staying the same? It doesn't expand.
yeah.
Area stays constant. And now the force goes up, they hit harder, and that makes the pressure go up. Can you see how this works? This is the introduction to what we call partial theory. Partial theory. Dealing with the box of air. And we know that there's some relationship going on between pressure and density which is related to volume. And all these things are happening as we can picture what the molecules are doing inside the box. But we have to be able to picture doing that. Your brain has to see this process. So do me a favor, grab a box with your hands. You have a box. Now, what's in the box?
Molecules.
Okay, first of all, do you have a box in your hands? Not a real one. Ian, in fact, totally opposite. What kind of a box are you holding? Everybody? What kind of a box is that? Abi?
Imaginary box?
So how much does an imaginary box weigh?
Nothing.
What's an imaginary box made out of?
Nothing.
Right? It's just your imagination. Okay. Do you see the molecules inside the box?
No.
Because they're invisible. Can you pretend that you see them?
Yeah.
And what do you see them as? Little dots. And what are the dots doing?
Moving around.
Okay. So imagine they're moving around and you're holding the box. Now I tell you, hey, dude, make the molecules move faster. When they move faster, what will they do?
They would expand the wall.
Well, before that, they're going to hit the walls harder, right?
Harder, yeah.
So that would make the pressure go up.
Mm-hmm.
So therefore, what would happen as a result?
The box expands.
Okay, so here's the first thing we need to write on here. Do you agree that if the molecules moved faster, they'd hit the walls harder? You agree with that?
Yes.
Okay, so then what I need to say is temperature is a measure of the average energy of the molecules. And kinetic energy is 1/2 the mass times the velocity of the molecules squared. Do you think this equation might be somewhat important? I'm thinking. So I don't care how each one molecule is, I'm just looking at the average, okay? And it's the kinetic energy is the energy of what? Of motion. So it's the mass times how fast they're moving, the velocity, squared. That's kinetic energy. And temperature is a measure of that. Would you agree, therefore, that if I were to make the gas warmer, the molecules would move faster? What would that do as a result? Make the pressure go up. And that would cause the box to expand. Write a conclusion of that. Everybody individually write a conclusion of what I just said. When you do what to a gas, what happens to it? Isaac, what are you going to write, Isaac?
I'll be honest, I could not retain what you just explained.
Do you see it? Take your gas. There's molecules moving in it, right?
Mm-hmm.
What did I say they have to do?
Expand.
Well, what are the molecules going to do? They're going to
move around.
But they're going to move faster.
Yes.
So the first thing is you're making the molecules move faster. Well, what is that? What do you call making the molecules move faster? Anybody?
Acceleration.
You're not wrong,
Would it be
but
changing
if I said the
velocity?
molecules are moving faster, what happened to the molecules? What happened to the gas?
Oh, they got hotter.
It got hotter. So you're making the gas get hotter. Is there an easier way to say that? What do you call the process of making something hotter?
Changing
Go ahead,
temperature?
Tom. You're heating it, right? So you're heating the gas. And when you heat the gas, what will happen?
Fuels move faster and cause the container to expand.
So when you heat a gas, the gas expands. That's what we're saying. When you heat a gas, the gas expands. So here's my box. Oops. Here's my box. I heat it, I make the molecules go faster, and the box expands. What happens to the pressure?
Stays constant.
Who said that?
That was me, Zach.
Back? Okay. Zach says it stays constant. Other Zach, what do you think?
I was going to say the same thing.
You think it stays constant, okay? Anybody say anything different?
And if it expands, it does stay constant.
So Jim, you're saying it doesn't stay constant.
Well, if it's expanding.
If it's expanding, what do you say then?
Wait, never mind. I take it back.
What if it's not expanding?
Well, the pressure just continues to go up.
What do you think, Ryan?
I mean, pressure go down because the area is going up.
So Ryan says, wouldn't the pressure go down because the area is going up? Lena, you're agreeing with that?
Yeah, I think you'd have to like add more molecules in order to like keep that pressure constant. So I think that it's increasing.
Nick, what do you think?
Yeah, that's honestly what I thought. I thought that you'd have to add more molecules to keep the like area expanding. But I guess now I feel like I'm wrong.
Anybody say it goes up?
I mean, that's what I thought. But
what happens to pressure? Does it go up, down, or stay the same? Aaron, what do you think?
Or down or same. She thinks the pressure goes up.
You think the pressure goes up? Well, which one is it?
Well, what kind of box are we dealing with?
So I've got a box of air. I want you to imagine in your head, right? By the way, I have come to appreciate in my life. What do you see on your screen right now?
Blackboard.
Blackboard.
You see Blackboard. Okay, good. So I'm not blocking your vision. That's so cool. All right, I thought you would see people. So here you are. Here's the box of air. I heat it, which makes the molecules go faster. That's what you have to picture. I'm making it hotter. They're moving faster. What happens to pressure in that box? It either goes up, it goes down, or it stays the same, right? Those are the only three possible answers to that
Can it
question.
go up?
And I've had people, everybody in here said something different. So discuss it. Let me hear how you come to knowledge about this.
Wouldn't the pressure go up since it's heating up and it's bouncing off the walls constantly?
Well, I thought the box was expanding, right? So wouldn't it be because pressure would go up, but that would cause the box to expand. But because the box expands, the pressure will go back down, keeping it constant.
What about like a hot air balloon or something? You put heat into it and it expands, and the pressure goes up, and you take heat away and it goes down.
See, this is so awesome because it could be a lot of different things. But what matters is, well, what else are you holding constant? See, it's a matter of looking at a change. You heat something and then say, well, what holds constant? So let's imagine this. Let's imagine that we heat the gas, but we hold the volume constant. We don't let it expand. As we heat the gas, what will then happen? The molecules are moving faster, so they'll hit with a greater force.
So
that force will be exerted over the same area, which makes the pressure go up.
Right.
But what if the box is imaginary? I hit the walls harder, you're saying it expands. And so as it expands, what's the area doing? That would make the area bigger. So some of you said, well, the pressure would go down, but they're moving faster. So the force and the area are both increasing and the pressure stays the same. So it depends on the box. If I have what we call a rigid box, meaning I don't let it change, then that's true. It's pressure goes up. But if the box expands, so the question is, I have a box of air, right? Here's the box of air. And do you agree that there's pressure inside the box? It's a three-dimensional box, so you could imagine a three-dimensional box, that's fine. But there's pressure inside the box because the molecules are hitting the walls of the box trying to get out. But do you also agree if it's imaginary and it weighs nothing and it doesn't have any structure, there must be air pressure outside the box. And the pressure outside the box, P out, is because molecules outside are trying to get in. What's the relationship between the pressure inside and the pressure outside? And the answer is, it has to be the same because there's no box. The pressure inside is always equal to the pressure outside. You need to write that down. The pressure inside is always equal to the pressure outside if there's no box, if there's no real box.
But when is there a real box though? I mean,
your tire on your car is a real box.
Oh, yeah.
Right now, the outside air pressure is, did I give you what the standard sea level pressure is?
It's 1,013.
0.25 millibars, right? Everybody, what is it? 1,013.25 millibars. What is it in PSI?
7.14 is that what that is? Or no?
14.7.
No.
14.7.
14. So in other words, you go outside in your car, you have 14.7 pounds of force exerted per square inch on the outside of your tire. That's the air pressure. That's what the air is pushing down at us right now. But inside your car, how much do you inflate your tires on your car? Do you know the answer to that? What does that mean?
PSI.
Mine's like 34, 32, 34 is what
34, 36, you know, I guess it depends on the size of your tire, but let's just say 36 PSI. So that means there's 36 pounds per square inch of air trying to get out, and there's less coming in. That's because what's your tire made out of? Hard rubber that doesn't change its size very rapidly. The more that you put in there, like you pump up a basketball. A basketball is a big round ball. You put more air into it, you're going to increase the pressure. It's not getting bigger. Now, eventually, it'll weaken and it'll explode. This is actually how hand grenades work, right? Hand grenades, you pull the pin, and inside this metal box of the hand grenade, there's a chemical reaction and the temperature goes up. And as that temperature goes up, molecules are moving faster and faster, and they're putting more and more pressure. And the metal can contain that for a while. But after a while, it's so much pressure inside, the metal fatigues, it can't resist that pressure, and it explodes. That's what's going on. You over pump a basketball, it will eventually explode. I think there's YouTube videos where you can actually see that. It's kind of cool. Just keep pumping. You have a pressure pump on a basketball and it explodes. It's fun, but that's a real box. This box in the picture here is imaginary. It's not made of anything. So that means as soon as you put more pressure in it, what will the wall do? It starts to move. It's like a push of war. It's not a tug of war. They're not pulling, they're pushing. And if the molecules inside get warmer, then the box expands. Does that make sense to you? So I heat the box, and as I take this, so watch what's going on from an equation standpoint. P equals F over A. So I heat it, the force goes up, but that would make the pressure go up if it stayed the same. But because the area is going up, and they're directly proportional if this is constant. So the pressure stays constant. Why? Because the outside air pressure stays constant. I'm only heating the air molecules inside the box, and that means the box expands. So what that means is when I heat a gas, it expands. The gas expands when I heat it because there is no real box. It's just a collection, it's an imagination. And it's always, the pressure inside is always equal to the pressure outside the box. Does that make sense to you? Okay. You have a video to go through and you can go listen to that discussion again if you need to, but that's because there's no real box. Now, when we talk about pressure, did I give you the working definition of air pressure? What did I say that working definition of air pressure was?
The weight of the air above us.
It's the weight of the air above you. Okay, so it is what it is. So basically what I'm saying is this, and Sam, we talked about this in severe, right? If I heat this gas rapidly, it expands, trying to keep the pressure the same. A gas, something that expands and compresses is called an expansion wave. Do you know what an expansion wave of air is called? When air expands and compresses, it's called sound. So what in the atmosphere can heat the air really, really hot, really, really quickly? Anyone else but Sam?
What, Aaron? Spell it out.
What could heat the air super fast, super quick?
The sun.
I don't hear you.
The sun.
The sun doesn't do it super quickly. I mean like super fast, like within nothing.
Nuclear bomb.
Okay. Let me rephrase the question. What could heat the air naturally super fast? Because yes, Tom, you're damn right. A nuclear bomb. How about lightning? Isn't lightning really hot? So what lightning does is it goes through the atmosphere and it expands the column of air where the lightning stroke is, and expands it. And that's what we hear as thunder. Because what's happening is this air adjusts to lower the pressure. Because I want to raise the pressure by heating it, but I need to keep the pressure the same, and so the box expands. So the answer is, now listen, I'm going to be technical here. The air pressure in the box is always equal to the air pressure outside the box. That's what I'm telling you to know. In reality, it takes time to adjust. That time of adjustment is the speed of sound. The air can only adjust so fast. So when the air has to adjust, faster than sound, it creates a wave, and then we call that thunder. If I heated it slowly, you wouldn't hear it. It would just expand. But if it heats faster than I can, then I can expand it. Then we hear a shock wave. That's called thunder. Make sense? So, did you write down when you heat a gas, it expands? Then write this right after that sentence. But what happens when a gas expands? It cools. When you heat a gas, it expands. But when a gas expands, it cools. Explain that. And I bet you
Particles aren't bouncing off of each other as fast anymore because there's more room in between them.
interesting. That's what people like to say, but that is not true. So what I want to do is, this is what we're working to. To get the answer to this is very hard, but it is foundational to how meteorology works. So I want you to think about it over the weekend. Seriously, I want you to be a science geek, and I want you to ponder this stuff and try to figure out the answer. Before we do that, I have to define something else a little bit more. Do you understand that the molecule is hitting the wall of the box? And that's the force. The harder it hits, the greater the force. But what is a force really? So what is a force? So I want you to imagine that I have a wall of a box, and I'm just looking at it. It's like Pong, okay? And I have a molecule that's moving this way, hits the wall of the box. What will happen to the molecule when it hits the wall of the box?
Bounce off.
It'll go and bounce off at the same, what?
Velocity?
No.
Or force?
Speed.
Speed.
It bounces off at the same speed. So if it's hitting, and I kind of told you this the other day, if it hits at 30 miles an hour, how fast is it going after it hits the wall?
30
miles an hour.
30 miles an hour. Is the velocity the same?
Yes.
What's the difference between speed and velocity?
Velocity is like the speed over time, right? Am I remembering that correctly?
No, so is speed. Right? Speed or velocity, according to the lab, is in a certain amount of time.
So
what's the difference?
Velocity has direction.
Velocity has direction. So like this number line, this guy is moving at 30 miles. Oops. This guy is moving at 30 miles an hour. This is plus 30. But when it comes back, now the vector, or now the direction, is in the opposite direction at 30 miles an hour, going in the other direction. So what is the change in the velocity if those are both in miles per hour? How different is this and this?
60 miles an hour.
60 miles an hour.
Right? The difference is 60 miles an hour. The speed's the same, 30, but it's going in a completely different direction. It means it's changed by twice the speed. So the force What does that mean? 3 of those, what does that mean? Zach, Medlin,
Can you say that again?
what does this mean, symbol?
The 3 lines. I don't remember.
We drew that. Do you have it in your notes from the other day? This is where, see, when I do something like this, I would not expect you to have memorized it, maybe, but I would have expected you to have it in your notes from the other day. So if you don't have your notes rewritten well, then I can find that out here. So, and I can't find that out. You have to find it out and go, I'm not doing well enough. So do you have it written down?
I'm looking.
And you don't have to admit this, but if you're going to be a good student, you have to say, I got this or I didn't get that. Ooh, I'm not doing well enough.
I might need you to repeat.
Lena, you do have that. What did you write down?
Yeah, it's like in science defined as.
Right? It's defined as. We're defining what a force is. Anybody know what this thing is called? Mass times the velocity? There's a name for that. Anyone? Aaron, do you know the answer?
Acceleration?
No. That's something called momentum. Mass times the velocity is called momentum. Right? Imagine that there's a kid on a tricycle and the kid's riding around at 5 miles an hour. Now that's really fast for a kid. Let's say it's 2 miles an hour and the kid runs into you. What do you typically do? You go, ow, that hurt, kid, get out of here, push him away, right? If a locomotive hit you at 2 miles an hour, you'd go flying. Why? The train has more momentum because its mass is so much bigger. It's going the same speed, but its mass is much larger. So force is, say this. Hold on. Say this. Everybody?
That's the question.
Okay, well, don't do that yet. Just say this.
Difference in momentum over the distance and time.
No, how would you say that? Remember, it's got the D in it, so how do you say that? I'm just asking you to say it.
Change in time.
Huh?
Change in momentum over change in time.
Well, I'm not asking you for the question. I'm asking you how to say that.
How
dmv dt.
You could say dmv dt, or you could just say d momentum d time. That's d momentum d time.
That's the question.
So now what is the question? How does momentum change over time? Okay, but here's the thing about that. The change in the momentum, when the molecule hits the wall, what part of this is not changing? What part of this doesn't change? Does the velocity change? Yes. Does the mass change? No. So I can rewrite that as saying this. Oh, sorry. I can say that's the mass times dv dt. dv dt. How does the...
That's the question.
That's the question.
How does the velocity change?
Over time.
Now, Aaron, what do you call the change in the velocity over time?
That's acceleration.
That's acceleration. So I get this equation, force equals mass times acceleration. The way that your velocity changes is called an acceleration. This, anybody know what you call this? This could be one of the most important equations in all of physics.
Oh, Newton.
That's Newton's second law of motion. F equals ma. Did you learn that in high school? Do me a favor. If you learned it, go like this. If you didn't learn it, go like this. See, if it were up to me, if I were king, and I'm running for king, so vote for me. Everybody would, no one could get out of high school without knowing certain things. We're going to do 3 of them in the first 2 weeks of class. This is one of them. Newton's second law of motion. F equals ma. So the fact that this molecule comes and changes is actually changing its velocity, which means it's changing its momentum, which means it's a force. Instead of going at 30 miles an hour, let's say it's going at 40 miles an hour, how much would the velocity change then? 80 miles an hour. That would fit with the greater force. Or it would take more force to change the velocity. But here's a cool thing. What's the formula for kinetic energy? Everybody?
Half mass times velocity squared.
When the molecule hits the wall of the box and bounces back, does the kinetic energy change? Is this molecule of a different kinetic energy? Different? Why not? Because what am I doing to the velocity? I'm squaring it. So the first velocity was plus 30 squared is 900. This, when the molecule bounces off, it's minus 30 squared, which is how much?
900.
Still 900. That doesn't change. That doesn't change. That's a half. So when the molecule hits the wall of the box, it does not change its kinetic energy. Now, Tom, listen to what I'm going to say to you. When the molecules hit each other, their average kinetic energy doesn't change just because they're hitting each other. So when you say, right, if the box expands, you say they don't hit each other as much, and they wouldn't, why are they colder? That's what you need to think about. But this thing here, just think, this thing here, I just want you to know, this definition of force becoming Newton's second law, I'm going to ask you to derive this on a test. So you better become comfortable with this stuff. Because you need to be able to explain it part by part. Okay? So it's on video. You can go back and you can look at it again. But that is what you're going to be doing. Before I erase this, do you have any questions on this for me now? Because you can go back and look at it again. Okay, scale of 1 to 5, how well do you think you understand this? I've got some 4s, I've got some 5s. Okay, so then the problem is, what level, when I ask you that, what level do you think you're at? Give me an answer. Level 1, level 2, or level 3? Right? So I should not find anybody who says they're at level 3. Do you know why? I haven't heard anybody explain it. So far in this class, who's the only person at level 3?
You are.
Right, because I explained it. Could you explain it to somebody else? Let's do this. Where are you guys? I want you to take the time. At least one person, if not two people, explain that in the rooms. Okay, go. Oh, I should stop recording this. Pause. Okay, here comes. Everybody will show up real quick. Here we go. Who did it in your last room, guys? Who did it? Abby?
Yeah.
Who did it in your room? Who explained it?
Oh, that was me.
Okay.
I explained it.
Of all of you people, who would be volunteering to explain it in words so that we can all hear you? Zach, you said you were a 3 the first time I asked you, so
Yeah.
why don't you go ahead and prove it?
So, can I use like the same numbers that you used in your like explanation of it?
Yeah, I mean, I don't care how you explain it, because obviously
Yeah.
you're using your own words, yeah.
So let's say we have like a marble and we have it hit a wall at 30 miles per hour. It will bounce back at that same 30 miles per hour, making the difference between the speeds or the velocity, because it has direction now, it would make that 60. And so if we take that force equation of the dmv over dt, we plug in that 60 for the v. And then since the marble didn't change any mass, we didn't gain any mass or lose any mass from that marble, we keep m the same. So we could put that m on the outside of the parentheses, and we get the difference in velocity over the difference in time. And because that's the equation for acceleration, we can simplify that expression into m times a, or mass times acceleration, and that gets us the force equation of Newton's second law.
Now, that is a good job, right? That's a good job. And when you get to that point, you realize that every time you do it in the future, you can come up with a new way to do it, maybe even make it better, right? That's what learning really is all about, is at some point you go, I understand this concept and I can do that. So how many of you play either softball, baseball, or golf? Okay. If you've ever played the game, like I'm going to use baseball or softball, some bats are better than others. So what makes a bat better? It's the same weight as another bat. You're hitting the same baseball. You're swinging at the same strength. Why do some bats make the ball go faster or go further?
I'd guess the composition.
What about it? What are you changing in that thing?
You know, what it's made of. You're changing what it's made of.
Because what's it doing though? In that whole thing, right? Do you agree that the bat that I'm swinging is there to impart a force on the ball? It's some weight, so it has a mass, and I can only swing it so fast, right? A different bat made of something different doesn't make me swing it faster. So I'm imparting the same force on the ball as I can. Do you agree? The difference is how long is that ball in contact with the bat? The shorter the time, the more the force is, right? Force is the change in the momentum, which I can't control, divided by the change in time, dt. So if it's made of a material that causes the ball to pop off of it, or you make the ball more poppy, then the ball will go further with the same swing. You're not changing anything. The ball just goes further. This is true of golf balls. Same thing. Better made balls will get off the club faster, and that means it's going to go further. You ever play softball? See, we're all from Chicago, right? So you have, what do you call the 60-inch softball that we play with?
A clincher.
It's a clincher, right? And you go elsewhere in the country and you bring a clincher, they'll go, what the hell is that? Nobody knows what a clincher is. Chicago, we play clincher. You get one out of the box, it's hard, right? You hit it, it goes really far, and it breaks people's fingers because it's just like this big monster ball. But after you play for it with a long time, what does the ball become?
It's soft.
It's soft and mushy. So when you hit it, it's like the ball gets deformed on it, and it takes you can't hit the ball as far anymore. That's because you're giving it more time. The greater the time on the ball or on the bat, the less of a force you're imparting. So that's just I just thought we'd throw that out there so you understand how these things work. Now, the last thing we need to do is finish the lab. Now, I think at this point, everything in the lab, read it, understand it. You should be able to get everything up to this point. However, who was it? Somebody just wrote to me. Who was the other person in the class? Julia. Sorry, Julia. Julia, I couldn't remember your first name. Julia has had computer issues, so she emailed me. So she had asked about doing the lapse rates. So the lapse rates, what I need you to do, and that's why you got the names, is contact each other and try to help each other out on that last part of the lab. Tom, you know, your brother in the class last time had a whole Snapchat group or something, or I think it was Snapchat.
Right.
So feel free to talk to each other to get the lab solved for that, but you're really just taking a look at the change in the temperature, which I give you temperature, and the change in the height, and I give you the heights. SFC means surface, so 0 kilometers. Surface is 0 kilometers, and then I give you the temperatures, and you calculate those. Then there's one where you go online to actually calculate a new lapse rate based on actual data from Jackson, Mississippi. So Sam, you might want to wait on it till Saturday, where you can actually get some actual good lapse rates up there.
Yeah.
So your calculating lapse rates, it'll give you the temperature, it'll give you the pressure, the temperature, and the height. And you want the temperature and the height, take the difference, divide it by the difference, and make sure you figure that out. So that is your assignment, is to finish that lab. Now, how did you do in the class so far today? You feel better? I mean, I hope you're learning. This is some serious heavy duty science. You're at college now. So from here on out, I expect you, when I give you an assignment, I expect to do well. So, and if I say, I want you to read this, that means take it seriously, even if you're not turning it in. Okay, now, before we go, am I sharing my screen? No.
No.
I want to show you one last thing, because I don't know if you've been paying attention to the weather, but if you take a look at this, the amount of moisture available with this system may lead to significant snowfall, with present models indicating amounts as much as more than 8 inches possible. And then the heavier snow moves east on Sunday, will wrap around light snow to persist all day Sunday. Total snow accumulations are looking to be around 10 to 12 inches of snow as of right now. It's still a bit far out there, but that's what's going on.
Better you than me.
Yeah, better us. And I don't think you're going to get a whole lot, but we're going to get a lot. So it's a pretty interesting snowstorm. And I don't even know. Hold on, let me see. What are they looking to do?
Are we looking at like a blizzard or?
No, it's a warm advection. So this is not a super windy day. Let's see what we got here, Roland. Here, DuPage. Got to move you guys. Tonight, mostly clear. Lows 6 to 10 above. It's cold. It's been cold. And then we have several inches accumulation. So that's what they're calling for as of this time. It'll probably be a winter storm watch soon. Then cloudy. And then Monday, lows 12 to 16, lower 30. So it's not super cold. We've been able to get away from the super cold weather so far. And the longer we go, like what's next Tuesday? What day is next Tuesday?
The 2nd, February 2nd.
Yeah, what's that day then? What do you call that?
Groundhog Day.
Groundhog's Day. So in the countdown to spring, because I'm a big spring guy, I like Groundhog's Day. The next one will be middle of February, which is what? What's special about February 15th usually? That pitchers catchers report. And then the next day is when spring training begins. Then we get to the equinox in March, and then opening day is the beginning of spring. In my world, spring is all about baseball. How many baseball fans do we have? I like baseball. Okay, guys, that is our class. Any questions before I let you go?
No, sir.
Okay, good job today in participating. I hope you get used to doing this because this is the way I want to do it. So feel more free. I hope to do that. Did you like the breakout rooms?
Yeah.
That help you? Okay, well, we got to do what we can. Stay positive. If you have a problem, email me. I'll respond to you. Okay? And have fun with the snow. See you all on Tuesday.
Before everyone leaves,
Have a good one.
I'm gonna send an email to everyone, and if you could just respond with your phone number, and I can make a group name, that would be cool.
Oh, that'd be cool. All right, so we'll do that, and you can kind of fun with that one. Okay, guys. Sam, I hate you. All right, we'll see you later.
Have a
Thank
good day.
you.
Thank you.
Have a good weekend.
Yeah.
Bye-bye. Oh, did you guys? Oh, you sent an email.
Yes.
Okay, sounds good. Hey, you did a good job, Aaron.
Great, thanks.
Good work. We'll see you guys on Tuesday. Bye.
Bye.